Hello everyone, myself Shobna Khedekar, and today I will be taking you through the progress of my research project on hybrid optical and radio frequency communication systems. So, what is the need of hybrid communication system? Imagine trying to send a message during a thunderstorm or thick fog. Radio frequencies degrade in rain while optical signals like research struggle in fog or snow. This is where the idea of hybrid communication system comes in, leveraging the strengths of the both. The RF here refers to radio frequency, whereas FSO is free space optical frequencies, and both perform differently in different weather conditions. The goal or the objective of my project is to model how signal drops in both RF and FSO links under various weather conditions using machine learning. Just as I mentioned a few seconds ago, we will be predicting predicting these RF and FSO attenuations, that is the power loss, using various predictive models under different weather conditions. And to compare these models, we will be using performing metrics like RMSE and R squared. RMSE is root mean squared error. We'll be building two types of models. That is, first would be trained on the entire data set, and second would be just weather specific, which I'll discuss later in detail. The data set we are using spans around six global cities and includes seven distinct weather types encoded using sign-up codes. Each condition is described using 25 atmospheric temperature parameters such as temperature, humidity, rain intensity, maximum temperature, minimum temperature, visibility, and etc. So due to the high complexity of our data set, we'll be using random forest model, which has various built-in features such as feature importance, and it also has the ability to capture the non-linear relationships within the data sets as well. So as you can see, the sign-up code here specifies particular weather conditions. That is, 0 means a clear weather, 3 refers to dust or stormy weather, 4 means foggy weather, drizzle is given by 5, whereas if it's raining, then that condition is denoted by 6, if it's snowing, then it's 7, and slight showers are denoted by 8. And the key variables or the variables that we will be predicting are FSO attenuation and RF attenuation. And this attenuation means the power loss, or how much signal is been lost during the transfer from one place to another. Right. To improve our prediction accuracy, we will be using feature selection or feature engineering. Random forest trains each decision tree on a bootstrap sample where approx 37% of the instances are left out of bag and act as a building validation set for that tree, which means that those 37% instances are not actually seen by the dataset while training. So it enables an internal error estimate without needing a separate test set or cross validation. Here is the algorithm for the out of bag error that we will be using. Right. So we will be exploring two main methods in this phase. The method one trains separate models as per weather conditions using the sign-up codes that I've showed you before. Method two builds a generic models that is taking in all the variables into account and building one random forest model for FSO attenuation and RF attenuation age. This term, we will be exploring method 3, Markov chain-based modeling, which is going to be my future work and has not yet been completely implemented. This is a probabilistic approach using Markov chains to model the dependencies between the weather conditions and the attenuation indirectly. I'll be talking about this in depth a bit further. So moving on to independent or weather specific models. In this, the data set is divided into subsets using the sign-off codes. That is, there will be a completely different data set for a clear weather that is denoted by 0. Then there will be a different data set for rain and so on. Then the random forest is trained for each of these models based on the sign-off codes. The advantage of this independent or weather specific model is to help us have more precise fit that is unique to each weather condition, and we'll be able to see the effect of each conditions on the RF and FSO attenuations. It will also give us flexibility in hyper tuning parameters as per the needs of each weather. The disadvantage here is that it is going to take a lot of time to build these models, run them, and then hypertune the parameters. And also, there is a major drawback, that is data imbalance. For example, if we have 100 instances for rainy weather, whereas just 20 to 25 instances for a clear weather, so that thing is going to modify or be a hurdle in our predictions, because the model will not be able to gather as much information for clear weather as it would be able to for a rainy weather. And the second method, which is a generic model, we'll be only building a single random forest model, for one for RF attenuation and then the other one for FSO attenuation. Features here will be removed one by one to see the effect of it on the RMSE and R squared values. And then the most important variables are retained for our final random forest model. Right, so here are my results for the generic models for RF and FSO attenuation. And we can confirm that rain impairs radio frequency performance, as it stands out as the second most important feature. FSO systems are significantly affected by visibility and scattering. Distances are the common features between them. These differences underscores the need to customize feature selection processes to align with the unique properties of each communication channel. Moving on to method 3, that is shown in this diagram, which uses the Markov chain model, as I mentioned before. In this cascading architecture, we will first be predicting the FSO attenuation using the various environmental features such as temperature, frequency, humidity, etc. And then this predicted FSO value, along with the other weather conditions, we will be building a second random forest model to predict RF attenuation. So this will allow us to model the correlation and dependency between FSO and RF channels, leveraging one to improve the prediction of the other. And this will be turn vice versa, that will be first predicting the RF attenuation, then using those predicted values to predict the FSO attenuation. And again, this method will be done as a generic model as well as for each weather condition depending on the sign-off codes. Here we'll be also using Pearson correlation to measure the linear correlation between the two variables, that is the original FSO attenuation and the predicted FSO attenuation values, and same for the RF attenuation. Finally, here are the results shown for generic models. as well as for the independent models. And the generic models offer a better explanation with R square scores over 0.95. Specific models slightly outperform on RMSE in some cases, but at the cost of complexity that I just mentioned before. This reinforces the value of using generic model when a balance between accuracy and efficiency is required. Okay. My future work, as I've mentioned, will depend on implementing method 3, and then hypertuning these parameters to achieve optimal results as possible. And this is just a reference for the image that I have used. Thank you so much.